For today's seminar, we have Dr. Erica DiFilippo present. She's a senior geochemist. And I'll just read a little bit about her background so you get an idea of what she's going to present today. Many hats, her experience as an environmental consultant. She has extensive experience addressing the fate and transport of organic and inorganic contaminants in the environment, conducted numerous studies of groundwater transport, statistical geochemical analysis, groundwater age dating, and dense non-aqueous phase liquid, or DNAPL as we call it, dissolution, enhanced DNAPL remediation technologies, and the use of innovative technologies for measuring in situ concentrations of organic contaminants in sediment, poor water, and has applied these statistical methods to evaluate background concentrations and the impact of site activities on groundwater contaminants. She has extensive experience coding in R and latex and has developed several R packages for data processing and analysis. And she's authored several publications related to organic and inorganic geochemistry and groundwater transport. So without further ado, I'll let her go ahead and get started on her presentation today.
Thank you, Candace. I'm glad to be here today. If you guys can't hear me, hopefully, I'm going to keep my mask on, but just let me know if it gets too muffled and you can't understand what I'm saying.
If you're comfortable taking it off, it would probably be helpful for the audio.
Okay.
Perfect.
Is that better? I can take it off. So the talk I'm going to give today is about my experiences as an environmental consultant. I think it's, a lot of times when, I know when I sat through these lectures in grad school, there's always a lot of talks about science, but how do you actually apply your science in your field once you get out of school? We didn't really get many of those talks. So that's what I'd really like to talk about today. I won't spend a whole lot of time on science. I'll talk a little bit about it at the end if we have time. But I'm really going to talk about what it's like, what you need to be an environmental consultant, what it's like to be an environmental consultant, kind of what are your day-to-day tasks, what are your kind of extraordinary day-to-day tasks, and kind of everything in between. So first, I'll give you a little bit about my professional background. I have a bachelor's in geology from Smith College up in Massachusetts. This was a really great experience being at such a small liberal arts college because we got a lot of hands-on experience doing geology. My senior thesis, we actually got to go to Greece and we looked at metamorphic rocks and these really cool blue schist rocks. So that's what we have here on the right-hand side is a thin section of the geochemical makeup of these different blue schist minerals. So kind of ever since grad school, I've been interested in geochemistry in some sort of way. So in undergrad, it was more hard rock geochemistry, and I've morphed into groundwater chemistry as I progressed. I have a master's degree in earth sciences from the University of Southern California in Los Angeles. This is where I really started to hone my skills as an inorganic geochemist, an organic geochemist, and also as a groundwater hydrologist. So that's kind of, those are the three hats that I wear usually on a daily basis, is my geology hat, my hydrology hat, and my geochemistry hat. At USC, I worked on developing or trying to understand the sources of water to a landslide surface. So there's a slide plain. This is just south of the city of Los Angeles on the Palos Verdes Peninsula, if anyone's familiar with it. They have a massive issue with landslides, and they slip on this really slippery clay, a bentonite clay. And so we were looking at sources of water to that bentonite surface to see if we could try to stop or slow down the movement of the landslide. So on the left-hand side is just a kind of overview of the kind of hummocky terrain of the landslide. The center portion here, in order to stop water from infiltrating the slide mass and making the slide mass heavier, they moved all of their utilities above ground. So these are actually the sewer lines for the community that lives on the landslide. And you can see that these shutoff valves used to be vertical, and with slide movement, they keep rotating towards the ocean. And the research that we did, I did some groundwater modeling, and we also did some age dating of groundwater to look at groundwater sources. So this is our apparatus for collecting chlorofluorocarbon, CFCs, from groundwater, which we were then able to use along with tritium, which is an isotope of hydrogen, to date the different water types that were impacting and infiltrating into the slide mass. From there, I moved to the University of Arizona, where I got my PhD in hydrology and water resources, and I also have a minor in soil, water, and environmental science. My research at University of Arizona was much more environmental contamination based. So we looked at DNAPLs and the relationship between the removal of DNAPL mass from a source zone and how that impacts the down gradient flux emanating from the source zone. Most of the work that I did here, I'd say the vast majority of work that I did at Arizona was actually laboratory based. So in the upper left-hand corner is a photograph of one of my experiments, these kind of sandboxes in the laboratory where we infiltrate DNAPL, which is dyed red so that we can see it. And then we developed a photographic methodology for determining the saturation of the DNAPL based on the color variations in the sand and in the dyed NAPL. So we could take a look at where the source zone mass was over time throughout the course of the experiment. And then we could take a look at the relationship between source zone mass and the flux emanating from the source zone. And following my PhD, I moved on to a postdoc with the US Geological Survey down in Reston, working for the National Research Program. This research actually brought me back into the field, and it brought me back to Southern California. We were looking just off the coast of Palos Verdes, where I did my master's degree. There is a large DDT contaminated sediment area which is being monitored as a Superfund site for the US EPA. So our research for the DDT contamination off Palos Verdes was to try to figure out a new way to collect pore water concentrations of organic contaminants. Typically what you do is you collect a core, you freeze it, and then you slice it, and then defrost it, and then kind of squeeze and extract all the water from it. When you do that, you lose all of the geologic information that you have from your sample and core. So if we can measure the concentrations in the pore water in situ, that could leave us the core intact for further evaluation for different types of analyses. So this research, again, brought me back out. I was in the lab for the most part, developing this methodology. This is SPME, or solid phase microextraction. So if anyone's familiar with a gas chromatograph, you have that large winding column. And the way I think of SPME is it's kind of a GC column inside out, right? So the GC column has a silicone the silica on the outside, creating the outside core of the column, and all of the coating is on the inside. With a SPME fiber, the fused silica is actually in the inside, and then the coating is on the outside. And the different coatings can attract different types of chemicals. In this case, we're looking at DDT. So we went out on a week-long research cruise from the Scripps Sproul vessel just off the coast of Southern California, where we collected sediment cores. We brought them back into the lab, and then we were able to, at discrete depth intervals, insert these microfibers, and then we were able to use those directly into the gas chromatograph to determine the concentration at discrete depth intervals within the core. Since 2010, I've been working with a small groundwater environmental consulting firm called SS Papadopulos. We're located currently our main office is located currently in Rockville, Maryland, so about 30-40 minutes away. Twin Brook area, if anyone's familiar with Rockville. The company was established in 1979 by Stavros Papadopoulos, who was a former USGS employee. So we actually have a lot of very strong ties to the USGS. Several of our employees either have worked with the USGS or worked at the USGS at some point in their career. We have about 70 employees in 8 offices around the US. Our main office, again, as I said, is in Rockville, but we do have offices in San Francisco, though that office handles more of our engineering. So if we're looking at remediation engineering or remediation technologies, that work is usually handled out of the staff at the San Francisco office. We have staff in Boulder, Colorado. We have a small, more field-based group based in Kansas City, Missouri. We have a modeling group that's located in Waterloo, Canada. And we also have some other minor offices in Portland and in Montreal as well. Our expertise is really groundwater modeling. That's kind of what built our company. We developed at SS Papadopulos MT3D. So if anyone's familiar with contaminant transport packages that are used in conjunction with ModFlow, which is the main groundwater modeling transport code, that was developed at SS Papadopulos. We've also helped develop and operate PEST, which is a parameter optimization software, which is often used in modeling. And we've aided in the development of ModFlow USG and ModPath 3DU, which is a particle tracking code. This is just the most recent version of the MT3D USGS code that was, I want to say it's a few years old now, but not maybe 2018, 2019, that was just released by the USGS. And a lot of the operating code, at least for the MT3D portion, was developed by workers at SS Papadopulos. We also do a lot of work with water resources. One of the most recent water resources cases we had was Mississippi versus Tennessee, which is actually a Supreme Court case from 2021. So that was actually a really fun day at work. Most of us took that morning off and sat and listened to the US Supreme Court arguments for this case. We were working for Tennessee. Mississippi was suing because they said that Tennessee was stealing their water. One of the really fascinating things about this is one of the main expert witnesses was a man named Steve Larson from our company. And a lot of the work that came out of that was used in the argument write-up for the final judgment in this case actually came directly from Steve's report. So it was really interesting to see how the work that he did actually significantly impacted a Supreme Court decision. We also do a lot of work with contaminant hydrology. I mean, we're environmental consultants. How do you not do contaminant hydrology? We have many different projects. I personally have worked on a lot of work at the Hanford facility, which is a Department of Energy facility in Richland, Washington. It's kind of very famous for making bombs during World War II. They have lots of different types of contamination. And we actually have a very strong geochemistry group. When I started, there were only about 2 or 3 real geochemists in the company. Since that time, we've actually ballooned, and we actually have a pretty significant portion of our technical staff that are actually geochemists. So we have a very strong geochemical component to the work that we do as well. So as I mentioned, I'm a geochemist. So what does a geochemist do at a consulting firm? Well, we do a lot of different things. And so this is just kind of you're not supposed to digest everything on this slide, but I want to give you kind of a sampling of all the different types of things that we have done as geochemists, specifically with my company. So we look at organic contaminants, we look at inorganic contaminants. We've done a lot of work with acid mine drainage when it comes to inorganics, perchlorate, oil and gas industry as well. We've had some projects where we've looked at fracking and the impact of fracking, PCBs, perchlorate, sulfate, nitrate. We've had projects where we look at the impacts of nitrate on groundwater. We also do some geochemical statistics. I spend a lot of time actually doing geochemical statistics. And that is really looking at compliance. Are our sites meeting the regulatory limits that have been set for them by EPA, or are the other regulatory agencies that are monitoring and are in control of these sites? And that's really, we really need to rely on statistics for that work to determine whether or not we've actually met the compliance that has been specified by the regulations. Also looking at background levels, when we look at inorganic contaminants, especially things like arsenic and lead, those are naturally occurring contaminants or naturally occurring elements, right? And they can also, so they can be naturally occurring or they can be contaminants. And it's really difficult sometimes to figure out what is a contaminant level and what is actually just a natural background level. Because sometimes arsenic is very high or very elevated concentrations in background. And so we could use geochemical statistics to help us determine what is the background for some of these elements in the natural environment, and then what would actually be considered to be impacted by some sort of industry. And that also goes with principal component analysis that's looking at the identification of sources and source contribution from different parties. We look at stable and radiogenic isotopes. So stable isotopes, we're looking at groundwater sources, groundwater age dating. We've looked at uranium transport and also different degradation rates. Monitor natural attenuation. If we have some time at the end of my talk, I'll talk a little bit more about this. I actually spend a lot of my time currently looking at or thinking about monitor natural attenuation. It ties very closely with the geochemical statistics because you need the geochemical statistics to really understand whether or not monitor natural attenuation is occurring and occurring at appropriate rates within your site. And so we look at, so I spend a lot of my time currently looking at that. We also look at some geochemical modeling. This is not my forte, but there are people in my company that do have this forte. So the main geochemical modeling program is FreakC, which again is another USGS publicly available code. And he's done many different studies where he's applied FreakC to look at fate and transport, aquifer storage, TDS transport. And finally, kind of the buzzword, emerging contaminants, especially from a, we do a lot of work for industry. And we also do a lot of work for lawyers, and I'll talk about that in a little bit. We do a lot of litigation support. As I mentioned, one of the cases or one of the projects we were working on was a case before the Supreme Court. And so emerging contaminants is a really important topic for us because as these contaminants start to be known and we start to see the impacts of these contaminants in receptors, people start to sue and we get lawsuits. And so we are often called in to take a look at some of these emerging contaminants like PFAS, dioxane, pharmaceuticals, 6-PPD quinone. That's always a fun one to say. So what does a typical day in my life look like? Well, this is my office. This is typically what I'm doing. I'm sitting at my desk. I've got a spreadsheet up. I've got Teams up because I'm usually talking to other people in my office or I'm talking to my clients. And I typically have R up. I'm a geochemist, but I use coding a lot to help me understand and to help me process data. Some of the sites that we have, especially the Hanford site, for example, they have 200 some wells where they collect transducer data, meaning they get automated water level measurements every hour. Over the course of a year, that's a huge amount of data. And you can't plug that into Excel and expect to be able to do any sort of processing of that data in any reasonable amount of time. So we really do rely a lot on code to help us process and understand our data. So what does an atypical day in my life look like? Well, a lot of different things. I'm fortunate. Our company is a very small company. As I mentioned, we've got about 70. We might actually have a little bit more than that, but definitely not more than 100 employees nationwide. And so being in such a small company, we get exposed to a lot of different opportunities. So we could be out at drilling sites. This is from a site that I was working on back in 2014, where we were looking at soil gas concentrations. And I spent months out in the field in West Virginia collecting these soil gas samples. We also, as advocates for our client, we also have presented at public meetings. This is a photo of the president of our company, Matt Tonkin. presenting at a public meeting in Minnesota, trying to relay relay the results of our research in layman's terms to the public so that they can understand what's happening. In this particular case, it was what's happening to lake levels. As I mentioned, we have a lot of work that is litigation work. So that requires us to testify, whether it's in their depositions or in court. But there are a lot of litigation cases where they do go to at least to deposition, if not to trial. And so that requires us to deal a lot with lawyers and to understand what to say and what not to say when speaking in court. As I mentioned, we also have developed a lot of different code. USGS, helping with the USGS mod flow, MT3D, the PEST course, or the PEST software. So we teach training courses. It's died down since the pandemic, but prior to the pandemic, every year we taught a training course, at least one training course in our office here in Maryland about how to use the PEST software. And finally, we do have some, not a lot, we do have some travel and even international travel. This is Charlie Andrews, who is the former president of our company. He has had a lot of experience working in China and working with some research scientists in China. Actually, the person who developed MT3D at our company has since moved on and was a professor at Alabama, and now is back in his home country of China, where he teaches. So we have a strong connection with Chinese hydrologists, and he's been asked to, on several occasions, to go and talk about policy and groundwater science. The work that we do is also very interdisciplinary. As I mentioned, we do a lot of litigation work. So that means we have to deal with lawyers on a fairly regular basis. We deal with drillers as we're out in the field. If I need to, for the work I was doing in West Virginia, we needed to develop a sampling plan, find locations, contact the drillers, make sure that they could do the work that we needed to do in the time frame that we needed them to do it. And we had to make sure and supervise them on site to make sure that they were actually performing the tasks the way that we wanted them to perform the tasks. We work with ecologists on several different sites, especially when we're talking about the impact of contamination on receptors, whether it's human populations or fish or ecological populations. We work a lot with engineers when we're dealing with remediation technologies in particular. And we work with mining companies when we were working on projects where we have acid mine drainage. We tend to work with mining companies as well. So it's very broad, all of the things that we do. And as I mentioned, it's very broad, all of the pieces that you have to bring to the table. No one ever expects you to know everything about everything. That's why we work so closely. I'm not a lawyer. I don't know all of the laws that are being applied to the different sites that I'm working at, but I have to work closely with them in order to understand what it is they need from me to show that we either have or have not met our remediation goals. So you have to wear a lot of different hats. It's kind of the whole point of this talk is you have your particular hat. You're a geologist, you're an engineer, you're an environmental scientist, you're a geochemist. But there are times where you have to expand a little bit. You have to be flexible, especially working in such a small firm as ours. You really have to be flexible and open to learning new things and getting involved in things that you didn't necessarily think you would have an interest in or be involved in when you started with a company. And so I've mentioned a little bit of some of the work that I've done, but just kind of to give you a final summary of a lot of the work or some of the work, as I mentioned, we have a connection with some universities in China. They usually, well, again, since the pandemic, would send a group of students to the US to learn about hydrology. They would typically come to our company and we would give them lectures about some of the innovative work that we've been doing in the groundwater field. So that's me giving a lecture to some of the Chinese students. Each year, my company has an annual meeting. Typically, that's somewhere here in the Chesapeake Bay area, where we talk about the health of the company, but we also talk about the things that people have been doing, some big projects people have been working on, any innovative projects that people have been working on. It's really important to, at least to the leadership in my company, that everyone still kind of keeps up with technology and keeps up with all of the things that are kind of happening in our field. And one of the ways we do that is we typically have some sort of technical group activity. This is me leading one on geochemistry, teaching them how to sample different components of seawater. It was a simple little project that we kind of came up with. I'm out collecting samples in the field. This is us collecting some PFAS samples in the summer of 2020. Again, some of the work that we do, we publish that work. And by publishing that work, we also present that work. So this is me at the waste management meeting in 2019, presenting some of the work we've done at Hanford. And then you get to do some cool things. Working at Hanford, we were working there's many different areas and many different reactors at Hanford. And we were working in the B area, and they offered us a tour of the B reactor, which is now part of the National Historic Site for the Manhattan Project. And it opened only a few years before. So we got to see what the old reactors, this is the first big, nuclear reactor in the United States is the B reactor. So sometimes you get to do some cool little things, like touring the B reactor. And one other thing I wanted to touch on, I've actually been having this conversation with my boss and another colleague, even in the past day or so, is professional volunteerism. There's a lot of things that I do from my 9 to 5, what I do for my projects, what I do for my clients. But there's a lot of other things I mentioned. Our company is really interested in keeping on top of all of the new innovations and technologies and topics that are always developing in environmental science, right? PFAS, 10, 15 years ago, no one really heard what PFAS was. No one knew what it was, but it has since gained momentum very rapidly in the environmental field. And you have to keep on top of these things. One of the ways you can keep on top of these is by doing some professional volunteerism. And I've been fortunate that my company supports professional volunteerism. So some of the two ways that I've done that is working with the ITRC, the Interstate Technology and Research Council. They develop these large guidance documents for several different topics. I was first exposed to them in grad school when we talked about DNAPLs. They have lots of different topics on DNAPLs and DNAPL remediation technologies. And so I jumped at the chance when they opened up their PFAS group to get on board with the PFAS group so that I could be involved. And what it really helped me was, there were lots of people in this group, and I could pick the brains of all of these different people that were experts in different areas, experts in sampling techniques, experts in analysis techniques, so that I could start to build my own personal knowledge that I could then apply to the projects I was working on. And I was fortunate enough to get a figure that I generated into the main PFAS document that was produced by the ITRC. Another organization I've been heavily involved in is the National Groundwater Association. There's lots of different volunteerism opportunities for NGWA, and my little plug for NGWA is it's free membership for students. So it's no cost to you to become involved in NGWA. And there's lots of different opportunities. They have scholarship opportunities. The Farvolden Scholarship is one that SS Papadopulos supports, that's given out to grad students who present at the National Groundwater meeting or summit at the end of each year. This is a photograph of myself and Charlie Andrews, our former president of our company. at the fly-in. So NGWA has a very strong interest in the politics of groundwater. And every year, their government affairs committee, which is I'm also a part of at the moment, comes up with some ideas that are really important for groundwater professionals. And the nice thing about NGWA is it's groundwater scientists, but it's also drillers and suppliers and all of these different things. And so we come up with ideas or topics that are really important to the groundwater industry. And we lobby the Hill, we lobby the members of the Senate and the House to benefit groundwater topics. So, I mean, one of the things we talked about was CDL license, truck driver license. For me, I don't care anything about CDL license, but for our drillers and our suppliers, CDL licenses are really important. So it's really interesting to see all the different aspects that go into the groundwater industry, not just the science. And yes, and that's me presenting the Farvolden Awards a few years ago. So I've talked a lot, glossing over a lot of the different things that you could potentially be doing or working on as an environmental scientist. But one of the things I want to touch on are the tools of the trade. As I mentioned, a lot of the times I'm in the office, right? Especially if you get higher up in any environmental consulting firm, you're going to spend more and more of your time in the office and less time in the field. Because quite frankly, the higher up you are in the company, the more expensive you are. And it's really expensive to have you out in the field collecting groundwater samples or collecting soil samples. So you're going to spend a lot of your time, especially as you develop your career in environmental consulting, in the office. And so what are the tools that I use? On a daily basis, I'm using all of the Microsoft tools, right? And I have them up here. And I mean, I know everyone knows them, but one of the things I wanted to touch on is why I'm using each of these different tools. What are the processes that I'm doing in my daily work that requires me to use these tools? Access, database software. We have to organize our data. I mean, one of the things that we spend a lot of time on when we initially get a project is building a database. It is really critical to understand how databases are built, how to organize your data, and how to extract that data in a meaningful manner so that you can then use it in your analysis. Because if you get junk in, you're going to get junk out whenever you do your analysis. Databasing is an extremely important part of the process that is often overlooked. Excel, I'm sure most people here are familiar with Excel. We use that a lot for data processing, typical stuff. I actually don't use Excel as much. I use it sometimes. I use code more often, but data processing, a lot of people do still use Excel. PowerPoint, communicating results. I just had a call yesterday with the EPA, the state of Michigan, and the potential responsible parties contractors, where I had to relay to them all of the results of a conceptual site model that we had developed for this particular site. Communication is a really important part of the process. If you cannot communicate your work, you're kind of dead in the water. No one's gonna believe you. No one's gonna understand what it is that you did. So you have to work. Communication skills are really critical in environmental consulting. Reports. Again, this goes right along with communicating results. I do a lot of report writing. And again, these have to be concise, clearly stated reports, whether they're being used by the EPA or they're being used by lawyers or they're being used by Supreme Court justices. These have to be clear and concise representations of the work that you've produced. And so writing reports seems like a trivial thing, but it actually is a skill that you really do need to develop. And I know that I thought that I could write reports when I first started working, and probably when I look back now, I'm like, those are not the best reports. But it really is a skill that you have to keep working on and honing throughout your career. And then working with clients, teams, not just presenting your results to your clients, but dealing with the quirks of your clients. I have some clients who don't know that much about the science that I'm trying to talk to them about. And so I have to learn to adapt the way I communicate with them so that I can relay the information that is necessary for them to understand for working with their site. I have other clients who are really aggressive and really abrasive. That requires me to figure out a different way to communicate with those clients as well, to get the point across that I'm trying to get across from my analyses. So all of these things are really important tools that you typically don't think about when you think about, what do I need to learn in school in order to get a job? Working with clients, organizing data, writing reports are things people don't typically think about, but they are very critical, especially if you want to move up in an environmental consulting industry. And as I mentioned, I use code a lot. I'm a geochemist, but I code a lot. Every day I'm coding. And coding for me requires a couple of different things. Visual Basic is how I started coding for my company. Visual Basic is a way to write macros into your Excel files, right? So you can automate a process or automate a plot generation using a VBA macro, but still being able to use Excel. The benefit of that is that I can very easily give that to the client, and they can open, they usually understand and know how to use Excel. And so I can provide information to them and provide analysis to them in a way that my client can also very easily open and understand. But in some cases, Excel is not going to cut it. And so I use R a lot. This is great for data processing, especially of large data sets. I do a lot of my geostatistics in R. And then LaTeX, this is a little bit of a touchy subject for me, but you can actually automate some of your report generation. So if you have a data summary report, say every quarter, you have to just summarize all of the data that you collected over the course of that quarter. It can cost a lot if you're doing it manually each time. But if it's a pretty prescribed method, right? You're providing the same tables, you're just changing the data in the tables. You're providing the same figures, just changing the data in those figures. You can automate a lot of that work and save yourself a lot of time. And there's a way that you can link data processing tools like R and LaTeX, which is a report generating tool, together to automate a lot of your report writing work for you for some of these very basic types of reports and types of data summaries. And so I've used those two together as well to generate some reports. The point I want to make about all of these tools and all of these coding languages is, especially at my company, it doesn't necessarily matter whether you're using R or whether you're using Python, but coding is becoming a much more prevalent piece of the puzzle when you're working in environmental consulting, especially when you start getting into these large data sets. To mention, the Hanford data sets are quite large, and even some of the geospatial data sets are even infinitely larger than the data sets we've been dealing with at Hanford. And you have to learn ways to process all of that information. And really the tools to do that are code. And as I said, it's becoming more and more prevalent. All of our young staff that are coming in, we are trying to get them up to speed in learning how to code. Again, the language isn't necessarily the issue. It's the thought process that goes behind coding. What I love about coding is not only does it fully document every step I've taken. When I'm processing data in Excel, I could copy and paste a column over, and then I lose all of the steps that went into how I came up with that number. But in code, it's all there. It's all documented. So it's a great way to keep track of all of the steps in your process. But it's also a really great way to organize how you approach a problem. In order to write good code and efficient code, you have to really think about what is the question that you're asking? How am I going to go about solving that or answering that question? And having to write it in code in an efficient manner is really, really helpful. for understanding the problems that you have and the questions that you're trying to ask. And so this is always my pitch whenever I'm talking to students is learn how to code, learn how to think as a coder to some extent, because the more you move on in the field, the more you're going to be dependent on having to know at least a little bit of code. And again, the language isn't necessarily the issue, but the process. How would you approach a problem using a coding language is really critical. And so if you have the chance at any point to learn how to do some coding, I highly recommend taking a course that either focuses specifically on coding or a class where one aspect of the class is about coding. And I have a little bit of time, we're going to breeze through the next set. I just wanted to give you an example of kind of some of the projects or some of the type of questions that we get asked as environmental consultants. And so one thing I've been working on a lot recently is natural attenuation and monitored natural attenuation. And so what does that mean? When we have attenuation, it means the natural transfer or breakdown of a particular contaminant of concern. And natural attenuation can be either a destructive method. So in red, we have our destructive methods like biodegradation, chemical reactions, or radioactivity. It can even be a mixing problem, right? Dispersion or dilution. Dilution is the solution to pollution, right? Or it can be a media transfer. So you can either sorb it from groundwater onto soil, or you can volatilize it from groundwater into the air. And monitored natural attenuation has a little bit of a bad connotation to it. So it's important to understand what monitored natural attenuation actually is. And it's a cost-effective way of restoring aquifers, where the immediate threat to the public is not, I wouldn't say does not exist necessarily, but is minimal. There are several different regulations that are and documents that have been produced by the EPA to kind of walk everyone through what monitored natural attenuation is. But the key takeaway is that monitored natural attenuation is not a walk away, leave alone strategy. And so in order for a monitored natural attenuation remediation strategy to be effective at a site, the rate of natural attenuation has to be greater than the rate of down gradient transport of your contaminants, right? Because you want to stop them from moving any farther in the aquifer. So they must comply with some of the EPA CERCLA, which is EPA, or RCRA, which is for active waste facility programs. And you want to minimize further migration of the plume and contaminants from the source zone. And you have to demonstrate that the approach that you're using is going to achieve the remedial objectives that have been set out by the regulatory agencies for your particular site. And M&A has a long history of use in the environmental field, dating back to the 70s, looking at controlled degradation in groundwater and the biodegradation of organochlorine compounds in groundwater. Even the National Research Council was talking about M&A as a practical cleanup methodology back in the early 90s. EPA, as I mentioned, has written many different documentation on the use of M&A and how to apply M&A at a site, dating all the way back to the late 80s through, I think the most recent publication was in 2015. And they recommend this 3-tiered approach for demonstrating that M&A is an appropriate remediation technology at your site. So the first is to demonstrate clear and meaningful temporal trends. So has the plume mass decreased over time, or has the concentration at your compliance points decreased over time? You can also take a look at indirect measures of natural attenuation processes, looking at sorption or dilution or volatilization. So some of these non-destructive M&A natural attenuation processes. And you can also show direct evidence that you have natural attenuation by looking at things like microcosm studies, looking at microbial degradation of your contaminants. And one of the ways we've applied this, I've talked several times that we've worked at Hanford, is looking at the 300 area in Hanford. In blue, we have the uranium contaminant plume. As you notice here, it's right along the river. Columbia River is a pretty large river running through the middle of Washington State. And in 2013, the record of decision that was passed from EPA and DOE for the site recognized that they wanted to use monitor natural attenuation for contaminants like tritium, cis 1,2-dichloroethene, nitrate, and trichloroethene. And so where we came in is taking a look at how do we determine whether or not monitor natural attenuation is really working for these particular contaminants. And one of the really difficult pieces about looking at temporal trends or how concentrations are changing over time is the really close correlation at the site between groundwater and surface water. So on the far left-hand side, I have a plot of groundwater elevations, which are in the black dots versus time. And on the secondary y-axis is the river stage versus time. You can see they're very closely correlated. When river stage goes up, groundwater elevations go up, right? We would expect this is only about 141 meters from the river. So this is not an unexpected result that there's this really close connection between groundwater and surface water. And how does that impact our contaminant concentrations? And I have that up here in the upper right-hand corner is our uranium concentrations on the y-axis and time on the x-axis. Again, the blue line is the river stage, and the green circles represent the measured uranium concentrations at this particular well. And you can see that every time river stage goes up, concentrations go down. And when river stage goes down, concentrations go up, right? It's a dilution effect, right? As water inundates, as clean water from the river inundates groundwater, you dilute the concentrations in groundwater that you extract from this well. And as river stage lessens and there's less of an influence of that clean water in the aquifer, your concentrations shoot right back up. And so how do we account for this when looking at temporal trends? We can make a trend line through all of this data, but all of this noise is going to create a problem for us. And when we try to predict what concentrations are going to be like in the future, all of that noise makes any prediction rather meaningless. So to account for that, we developed a censored regression, multiple regression analysis. And so now we can use multiple different variables. So typically when you do a temporal trend, it's concentration versus time. Now we're doing concentration versus time and river stage. And so by adding in that piece to the puzzle, we can account for the vast majority of this variation that we see in concentrations. And this blue line here, if you can see, is the average annual concentration that's been projected based on our trend analysis. And the blue band is the confidence interval in that average concentration. And when you compare that to typical trend methods, the Thiel-Sen method, using all of the data, or a Thiel-Sen method using only a seasonal subset of the data, so only looking at high river stage or low river stage, you can see that the confidence bands on our average concentrations are much tighter than they are using typical trend analysis methods. And that gives us a better predictive power for understanding whether or not we're meeting remedial goals. And so with that, I will end now. If anyone has any questions, I've talked about a variety of different things, so please feel free to ask me anything.
find it different when you're working for lawyers that work for companies than working, say, for EPA? Like, I used to work in consulting, and it seemed like they had these different expectations, and you had to kind of walk this line down the middle. There's a gray area. I don't know. Can you talk about that?
Sure. I think that really goes into the point that I was trying to make about communication and understanding who your client is and what your client's goals are. Even within EPA, we have a variety of different project managers that have different goals and different technical backgrounds. So dealing with lawyers, sometimes you're going to have lawyers that don't have a good, strong technical background of the science, but they know the law like the back of their hand. I've had experiences where we actually have some lawyers that do have an environmental science background, which makes discussing the technical work a little bit easier. But you really do have to adapt. And I think the key to adapting to your different clients, whether they're lawyers or they're technical consultants, or they're technical project managers at EPA, is understanding what their goals are, what their level of knowledge and interest is even, and really trying to adapt that. And that's a really hard skill to understand. It really is. And it takes a lot of time. It does a lot of growing pains to learn that set of skills. But it is really important, especially I know that there are some companies that solely work on government contracts. So your client is only some government bureaucrat. Our company, we don't work that way. We will pretty much work with anyone if we can, as long as we think that the science and the story is interesting. And so when you have that diverseness of clients, it really is a difficult skill to learn. And the way I learn it is by observing my higher ups, observing my principals. One of the nice things about, as I said, our company is a little bit unique to some other larger consulting firms, is that all of our project managers are technical leads. We don't have project managers that only kind of manage people. So when we have a big project and we need to talk to a lawyer, we need to talk to EPA, the person leading that, usually one of the higher ups, is also heavily invested in the technical work as well. And so trying to learn from them is really important. And that's one thing that we get a lot at my company, is we do get introduced to the client a lot. So sorry, that was very long-winded.
Thank you very much.
Sure. Yes.
So you obviously made a big pitch for students learning to code.
Yes.
Looking back on your graduate school days, is there anything you really wish you had done differently, preparing for where you are now?
I wish I had learned coding earlier. I had one class where we had to learn to code surface water class, and I kind of ended up blowing off some of the coding stuff at the end because it got really complicated and it was well above my level of knowledge at that point. And I didn't really persevere with the coding portion of that. I wish I had, because all of the coding I have now, I pretty much had to learn from scratch when I started with my company. And there are a lot of growing pains. Even now, I wrote an R package to do all of that trend stuff I showed. And just last week, I took some technical development time to repurpose it a little bit, because I went back and looked at it and was like, oh, this is maybe this is a little too clunky, or there's a better way to approach this. It always happens with code, but I wish I had paid a little bit more attention to some of that, because it is really important. And it is becoming increasingly more important in our field. Yes.
I have time for one more question. Yes.
Thank you for your presentation. My question was that do environmental scientists need to have professional certificates like PE or those?
So in some cases, yes. It definitely does not hurt to have your PE or your PG. I don't have mine, but I know that for some of our projects, when we write reports, I think for some projects that we do in Mississippi, for instance, we have to have a PG sign off on the report. So we have some people that are PGs, but I think it is a good tool to have, and it's also a good marketing tool for yourself as well.
think because of time, we have to wrap it up here, but thank you again.
Thank you.
For a very interesting presentation.